Hey, good morning, everyone. I'm Waqas. I'm an oncology fellow at the University of Chicago on our monthly podcast for our Oncology Data Advisor series on AI and oncology. We have a special guest with us today, Kevin Brown, who's the founder of Standard Model Biomedicine. Thanks so much for joining, Kevin.
Yeah, thank you so much. Thank you so much.
Yeah. I know it's AACR weekend. You got a busy schedule and a lot of things, going on. Maybe sort of briefly tell us about yourself and what Standard Model Biomedicine focuses on.
Yeah, absolutely. I was previously led foundation model development, like large scale AI, at Bristol Myers Squibb. And then while I was there, we saw firsthand during our time in oncology research how fragmented data and bespoke models sort of slowed progress. So we founded a standard model biomedicine to build multimodal foundation models that unlock, electronic health records, radiology, pathology, and other data at scale, so that every AI tool in medicine can stand on the same robust backbone and be used by domain experts for downstream tasks.
Got it. Got it. Thanks for sharing that. And I was kind of looking at your company and the problem state that you all listed. And I'm just going to read it right here. It says biomedical AI is too hard. The data is siloed, compute is too expensive, domain expertise is too important. So I think it's good for us to maybe take a stab at each of these problems to better understand sort of how your solutions and foundations model come in. Since we have kind of a general oncologist physician kind of audience, can you just briefly explain what a foundation model is before we get into all the different issues?
Yeah, for sure. So a foundation model is just a massively pre-trained neural network. You can think of it like a pre-assembled brain that's learned patterns across millions of medical records, radiology images, or pathology slides. And instead of building, trial or problem specific AI from scratch, you just take this model and fine tune it for your task, which slashes development time, reduces the reliance on bespoke data sets, and it really democratizes access to state of the art performance. You could think of it like how a human, learns general intelligence over the course of, human development and schooling, and then you may specialize, for instance, into an oncologist as you age. Artificial intelligence models can work the same way.
Got it. Okay, great. And so I think we can sort of dive into the first problem that you mentioned about siloed data across healthcare networks and biomedical teams. So I think from a doctor's perspective, it's pretty obvious when you go into Care Everywhere, have to search through Epic, you see a lot of different ways the data is displayed. Sometimes labs aren't shown the same way. Obviously, with notes, there's a lot of fluff from what's being generated from the computer, right? So there's a lot of disparate data. But maybe from a developers or startup angle, how do you kind of sort of deal with this problem?
Yeah, we think about it in two ways. So the first way is just how data is siloed. Like, hospitals and labs or large pharmaceutical companies will store data in different formats, proprietary platforms, or behind institutional firewalls for good reason. So our approach uses sort of a federated and privacy preserving training so that a single foundation model can learn across all of these different silos.
Mm,
We also find that expertise happens to be siloed, right? Even within the domain of oncology, you might have a lab, for instance, at a major academic medical center like the University of Chicago that focuses on artificial intelligence for radiology images, and another group that focuses on genomic sequences, and another one on the transcriptome. And incorporating all of these data together is super important to get a full picture of a patient, right? Even on a machine learning or AI level, we know that a patient is more than just the sum of the measurements you make. It's how they all fit together.
got it. And of course, putting together all this different data isn't cheap. It costs money. I think that's the thing that providers probably aren't as aware of, right? You got a chat GPT or Claude, and you just enter something and you get a response in a few seconds, right? You don't really think about the costs or all the different steps that are going on. And there's a lot more awareness now, I think, about the like computing costs, about the carbon footprint of LLMs and AIs. But maybe tell us a little bit about what are the computing costs looking like? Where are LLMs actually stored? How are they housed? Where are the data centers? Give us a sense of that.
Yeah, that's a great question. It sort of has two polar opposite answers. So training a large language model or another foundation model from scratch, can cost hundreds of millions of dollars. But running these models is orders of magnitude cheaper, and that's one of the advantages. So if you wanted to build a state-of-the-art model, you don't need yourself to go collect all of this data and then train it and then point it to your specialized use case, right? Which may be something pointed at, for instance, metastatic breast cancer. Um, on the other hand, like actually running these models can be quite cheap, which is how, ChatGPT, for instance, can, cost hundreds of millions of dollars to produce, and then, fractions of a cent in order to give you actual inference when you type into it.
Got it. And you mentioned earlier about how there's not just separation of data, but also about between experts as well, and kind of having to put them together. So what's the domain expertise problem in creating AI solutions?
Yeah, it's I think one of the most important things and one of the key reasons why we formed this company, which is that biomedical AI really demands a nuanced understanding because patient treatment and care or even clinical development really requires a nuanced understanding. You need to know how lab values correlate with outcomes, which imaging artifacts to ignore. In breast cancer, for instance, in dynamic contrast enhanced imaging, you might have background parenchymal enhancement that you're not going to have in CT. And you need to know how treatment protocols differ by region and demographics. And so foundation models can absorb these broad clinical patterns, which cuts down on sort of back and forth, but also they can be platforms on top of which domain experts can build those last mile solutions.
Mhm.
And we find that, 90% of biomedical AI is reasonably the same. You have a lot of patient data, which may come in different forms, and you collect it and you make some sort of representation that you can use to predict outcomes or progression or adverse events.
Mhm.
But that last 10% takes 90% of the effort and 90% of the expertise. Uh, we've found, for instance, in the course of our careers, that it's easy to get a surface level understanding, for instance, of an oncology patient and lab values. But when you speak to an actually practicing clinician, you know that these things all have to be contextualized in the rest of the patient history and the patient trajectory. It's not enough just to say, oh, here's your age, here's your, smoking history. There's a lot more to it than that.
Oh yeah, definitely. And the FDA actually put out some draft guidance on AI and drug development, actually just a few months ago in January, and they talked about sort of this idea of COU, or context of use, and kind of just being able to specify and validate different AI models for certain applications, and kind of making sure it works for that specific one. And also this idea of like a model risk matrix. So you talked about sort of predicting adverse events. So if there's an AI model, how much is that AI model contributing to the decision about, is this drug going to cause adverse event or not? And then what's the outcome, right, of a missed event, right? So if we make the wrong decision about adverse event prediction, maybe you have a patient who gets sent home after getting a new medication for outpatient monitoring, but they should have been monitored inpatient. That can obviously be catastrophic.
Yeah, 100%. And I think that those it just reinforces the point of domain expertise because those decisions have to be owned by healthcare practitioners because they're the ones that are responsible for the interface with the patient. And at the same time, they're probably not going to be collecting all of this data and training it at scale. So foundation models are sort of the interface between them that lets them move really quickly.
Right.
Um,
Yeah, yeah, that all makes sense. And so we talked a little bit about these issues about silo data, cost, and the domain expertise. So kind of moving on to solutions, what you guys are working on. Tell us about next event prediction. Why you designed it, and sort of what's exciting about it.
Yeah, what's really awesome about it is if you think about the way that, ChatGPT was trained, the
Mhm.
backbone of that was take a bunch of sentences and predict the next word. And in doing so, you get a really good understanding of language and reasoning. Next event prediction is kind of like that, but applied to patients. So you can imagine a patient can be contextualized in their history, the visits, labs, medications, other interventions that had happened, and you can forecast the next clinical milestone. And that could be tumor progression, that could be an adverse event, a hospital readmission, or an overall survival event, for instance. And so we're excited because it shifts us from reactive care to proactive intervention. An oncologist could get an early warning signal, could
Right.
do risk triaging, for instance, in radiation therapy for cardiac adverse events.
Right.
And at the same time, in the clinical development landscape, you can say, hey, look, is this cohort of patients going
Mhm.
to evolve in a particular way? How can we optimize clinical development to meet those unmet needs?
Right. Okay, got it. And maybe you kind of alluded to some examples already, but maybe let's take one practical example. Let's say you're an oncologist in the clinic, you have a lot of patients, and maybe there's a patient you're worried about, like for a certain adverse event, or febrile neutropenia, or risk for hospital admission after they get a new treatment, or after they have certain lab values. I mean, how would next event prediction or NEP kind of come into play, like for a busy clinician?
Yeah, that's a great question. So using a model that is trained on NEP specifically, like out of the box, probably is not the best thing. The best thing is probably to work with AI teams that exist in academic medical centers to make a tailored solution that is context aware of the particular unmet needs that happen. But practically speaking, this could be, hey, based on the history of events that have happened, you're highly at risk for a particular, adverse event if you go a certain route, right? If the intervention was radiotherapy, well, let's think about the adverse events that could happen there
Mm,
and whether or not the risk makes sense versus other interventions.
got it. And just going back to the busy clinician, a lot of oncologists are aging. About a quarter of oncologists are above the age of 65. But obviously, there's a lot of excitement about AI, trying to integrate it within practice. What advice do you have for oncologists who are trying to find ways to use it to help patient outcomes or use it in the clinic?
Yeah, I think the best thing to do is to collaborate with uh, AI, domain expertise, but like AI specific people that exist in academic medical centers because they'll have the ability to bridge the technical side into the actual unmet needs that the clinicians see. And I think emphasizing this point about, aging oncologists, we're going to have a lot more cancer patients, in the next 25 years, but the number of oncologists may not rise at the same rate. And so, reducing workload, whether that's clinical trial matching, I think it takes probably 40 minutes to assess whether a patient meets the IE criteria for a particular trial. And that's hard to do. You could imagine a situation that flags patients who are likely to benefit or likely to become eligible for trials even ahead of time would be awesome.
Yeah. And what are some use cases that we can expect to see, like from your team or within oncology in the coming year or two?
Yeah, I think in the coming year or two, one place where we're really excited is in these low risk settings where we can run sort of in shadow mode alongside oncologists, right, without actually driving the intervention itself. But for instance, in saying, hey, here's a risk profile for a particular patient if you went with this particular intervention, and then actually tracking those outcomes according to what we had predicted. I think at the same time in clinical development, it can be used to understand across the broad clinical landscape what these clinical patterns are. Are there perhaps better inclusion and exclusion criteria? You could do more efficient trial design that streamline and directly addresses patient needs.
Awesome. And one question we asked all our guests when we close out: what's your information diet like? What do you like to read? How do you keep up with things? There's obviously so much coming out every day. So what do you do personally?
That's awesome. So the first thing I do is I listen to podcasts like this because you gain a lot of sort of informal knowledge that points you in awesome directions and gets sort of this zeitgeist and undercurrent flow of what's happening. We also balance primary literature, Nature Medicine, JCO, um, reading to really understand the medical context, and then we also look at what's happening on the purely technical side because every week it seems like there are more advances in AI, and keeping up with them is difficult.
Awesome. Thanks so much for taking time to join today, and all the best with Standard Model and everything you guys are working on.